So we can start, no? Now only 45 people joined.
Yeah, you can start since anyway it's being recorded. They can revisit the first 5-10 minutes if they miss.
Okay. So good evening, girls. So today we'll be doing relativistic mechanics. So now to understand relativity, as a tradition, we'll go from the basics, how it was evolved and what are the principles behind it. So now, what is, if you have a coordinate system? Now, what is a coordinate system? It is just used to specify some point. If you have a point P, how to specify the location of that point P? We need some coordinate system to locate the point P, right? So we can write, if you have a point P, we can drop a perpendicular to the system and find out it is at x distance away from x-axis, y distance away from y-axis, and z distance away from z-axis. If the axes are like this, x, y, and z. So now this coordinate system can be thought of a frame of reference. Now, with reference to the origin, what is the location of the point P? So we can call the coordinate system to be a frame of reference. So it's a coordinate system used to locate some points. Now, if we know the frame of reference, then we have something called as inertial frame. Now, consider an observer is at origin. We have an observer is at origin. Now, consider the observer is moving. That means the origin itself is moving. That means with respect to him, that means according to him, the whole coordinate system itself is moving, right? Like if we have a coordinate system like this, observer is in the origin. Now, if the observer is moving at a velocity v, only the velocity v, if he is moving in the x-axis, if we specify the coordinate at the velocity vx in x-axis, then the whole coordinate system, that is the x, y, and z axis itself will move, right? Like after some time t, it might come here. After some time t, it could be here. So if this is the O is the original location and O dash is the final after some time t, if that is the origin, then at some time t, what happened? The reference system itself moved. So if we say that there is no acceleration, if there is no acceleration applied to the reference system, that means if the observer is moving at a constant velocity, that is velocity is not changing, then we call such reference system to be inertial frame of reference, or you can call it as inertial frame. So what is inertial frame? It's a reference system moving without any acceleration. That is, there is no force acting on the reference system. So we can tell if A is 0, that is Ax is equals to 0, then that reference system is called as the inertial frame of reference. Now, if we know inertial frame of reference, Galileo, what he did was, he found out how would the relation be with respect to the final reference system, that is after some time t, and what is the reference system which was in the original time. That is when time is equals to 0, what was the place, what was the reference system, and after time is equals to some time t, what was the reference system. He found out some relation. So that is called as Galilean transformation.
Sir, I have a question, sir.
Yeah.
Is Earth a inertial frame of reference?
So inertial frame of reference means there is no acceleration applied to the frame of reference. That is the one who is when the reference system is moving, there is no acceleration in that reference system. That is, the velocity is a constant velocity. So that is inertial frame.
I'm actually saying, is Earth a inertial frame of reference?
Earth is having centripetal acceleration, right? it has some acceleration, so it is not an inertial frame. It has some centrifugal force and centripetal force acting, and there is acceleration in the, and moreover the direction of velocity is changing, right, for Earth at every time.
Made
That's why it is.
for observations which we made on different laboratories around the globe, then the value and calculations will vary.
I'm not able to hear correctly.
I'm saying that if Earth is not inertial frame of reference, then the calculations which we made during different type of experiments, it will vary because it is, if it is not considered as a inertial frame of reference.
See, if we are doing some experiments on Earth itself, where Earth itself, with respect to us, Earth is not moving, right? So if we are standing still, for us, Earth is not moving. So whatever experiment we do in our inertial frame of reference in Earth itself, for us that reference frame is not moving, right? See, if you have your computer in front of you, is the computer moving with respect to you? No, because we Earth computer is all at one state, that is, it is not moving for us, right? So that's why the experiments won't vary if we do the experiment on Earth. By chance, if there is a frame of reference in outer space, and with respect to Earth, if we are doing some calculation, then there is some change. Because for a person who is out of Earth, for him, there is some acceleration which is observing in Earth. But for us, there is no acceleration.
Okay, sir. Thank you, sir.
Okay. So Galilean transformation. So there is very simple set of equations what it tells. So if we have a reference system here, we'll just specify two frames, that is x and y, and it is moving at a velocity v. After some time t, it came here. So with the velocity, it is here only. It's here, and the distance what the system moved is vt, right? At a time t, it will be v into t. So this is the origin o dash, and this is origin, initial origin. So if you have a point p, now if there are two observers, that is one observer is in this, one observer. Okay, let me. There is one change we have to do. So we have one observer who is in O reference system. Okay, one observer who is not moving, he is standing still. And there is another observer at O dash, who is moving. Okay, so O dash is the moving reference frame. O is the standing, that is the still or stationary reference frame. Okay, now if they both observe a point P, if there is some point P where both are observing it, so with respect to O dash, this is the coordinate, right? It will be like x comma y. Okay, sorry, here it will be x dash and y dash. So the value will be x dash and y dash. So the location of P according to the observer at O dash is x dash comma y dash. With respect to the observer who is at O at this reference frame, for him it will be x comma y. The same point P, this point P will be at x comma y for him who is at a stationary reference frame. So what would be the value? What would be the relation or the relation between x and x dash? That's what Galileo gave. We can easily derive that if this is Vt and this is x dash, so and the total for the observer at O, for him the value of x will be this, right? So this whole thing will be x for him. So what is x dash? X dash is equal to x minus Vt. And y, now it's not moving at y, no, it's only moving at x-axis. So at y-axis the velocity, there's no velocity, it is vx actually. So y dash is equals to y, it remains the same. If we have a z, even at z coordinate it is not moving, so z dash is equals to z. And Galileo, what he told, another principle is time is universal in all reference frame. So time, the value of time, it is universal. So universality of time. He said that time is constant or it doesn't change for different observers. So we can write t dash is equals to t. Okay, so this is called as Galilean transformation. Now, according to Galilean transformation, if the particle is having some velocity, if particle is having some velocity ux, then what would be the velocity of the particle for an observer at O? It would be so what would be the velocity of the particle at for an observer at O? Then we can find out the velocity, that is d by dt of x dash is equals to d by dt of what is x dash? X minus vt. So it is dx by dt minus v into dt by dt. Now why we can take out of the differential operator is because v is a constant, isn't it? Now we told that v is constant, that is the frame of reference is not having any acceleration. In an inertial frame, v is constant. So we can take it out. It will be what? Now if we say that dx dash by dt is the velocity of particle for an observer at O dash, his reference frame is at O dash. For him, the velocity is dx dash by dt. Let us call u dash is equals to dx dash by dt. So u dash is equals to, and similarly for an observer who is at reference frame O, for him the velocity of particle is dx by dt. So it is u minus v. So this is 1. So this is 1, right? So this is velocity relation. That is the relation of velocity between two observers. Okay. Now, if the particle, consider the particle P is accelerating in x-axis. Not the reference frame is not accelerating, rather P is accelerating. Then what is acceleration for a person who is at reference frame O dash? For a person at reference frame O dash, for him acceleration ax is equals to du dash. So let me write u subscript x everywhere because the change is always in x-axis in our case. So du x dash by dt is equal to, okay, if this is the acceleration of the particle for an observer at O dash, then for observer at O, for him the acceleration is okay x dash, sorry, for an observer who is at O dash, for him the acceleration is a dash x. Okay, dash is just to specify that the observer is measuring it at O dash. So for at O it will be ax, which is dux by dt. So if we differentiate this equation, if we differentiate, what we'll get? Dux dash by dt is equals to dux by dt. Now the v vanished because v is a constant. So with respect to a constant, it is 0. So what we'll get? We'll get ax dash is equals to ax. So this is acceleration relation for an observer who is moving, that is the frame of reference is moving, and for another observer whose frame of reference is not moving. So if this is Galilean transformation, Einstein found some faults and there is some history behind it, and he did some, he may imagine some principles and he put forth his principle of relativity. Now, according to Galilean relativity, Newton's laws are same in all the frame of reference, and time is a universal constant. So what he said, Newton's law, so Galileo what he said, Newton's law is same and time is universal. So time is universal and Newton's law is same in all frame of reference. This is Galilean relativity principle. But Einstein, what he told in his principle of relativity, in Einstein's principle of relativity, he told that he put forth two principles actually. One is the laws of physics. The laws of physics remain the same in all inertial frames. In all inertial frames. So what does this mean? It means that if a person is doing an experiment in his inertial frame, the values, that is the law what he'll apply in his inertial frame, will be the same to an observer who is applying the values in a stationary inertial frame. So if a person is moving, that is O dash, if it is moving, and for a person who is doing the experiment in that inertial frame itself, where he is doing the experiment in that moving inertial frame, for him what laws it applies, it will be the same for an observer who is at a constant place. That means is stationary. For a stationary observer, it will be the same. So that's what Einstein said in his first postulate. So in his second postulate, what he told was, he told that the speed of light in vacuum is the same for all observers in all inertial frames. That is universality of speed of light. Let me say it as C. That means the value of C is same for all observers, regardless if they are moving or constant or stationary. Regardless of that, C is same for all observers in inertial frame. Now C in vacuum, okay? C in vacuum. So this is Einstein's principle of relativity. Now Vikrant will take over and he'll continue with Lorentz transformation and all. Okay, so thank you.
Thank you, Sagar. So are there any questions related to whatever Sagar has done so far? Let's try to keep them short so that we can continue over. But are there any quick questions? Yes, go ahead.
Yeah, I have a doubt regarding the first principle, that laws of physics remain same. So what exactly here we are talking about if we are saying laws of physics? Like in
Alright.
inertial, if there are two inertial frames, one is stationary and another is moving with constant velocity, and an object is moving with some velocity. So for the two frames, the relative velocity with respect to these two frames will be different. So how are we saying that laws of physics?
Let me get to that. Let me just share my screen. Please let me know if you can see it, and I'll just read it out for you. I hope you can see my screen.
Yeah.
Right. Okay. So let me just make a new page for this question. All right. So okay, actually I'll just use this. Okay. So we have the two frames of reference here. I'm going to switch my color to say blue. Okay. We have two frames of reference, and this frame that is called y prime, x prime, and z prime is moving to the right along the x-axis with some velocity v. All right. Now, when you simply work out what the equation of motion is going to be with Galilean relativity. So with Galilean relativity, what you had was basically x, let me change the pen rather. X prime is x minus vt. That's what the Galilean relativity is telling us, right? Now, it is with just this much that we deduce that the laws of physics are going to be the same. Now, back before Einstein, right? Before Einstein, if you consider classical systems like these, the only laws of motion, laws of physics that you had to worry about were the Newton's laws of motion, about the law of inertia, about the second law, which says that F, the force applied, is proportional to momentum, or the more famous form that you know, which is F equals ma. Right? Those are the things that were more important that had to be satisfied. Now we can find that out here. All right. Now, why we call a frame inertial is because in both the frames there is no acceleration that is happening of the frames themselves. All right. So we'll differentiate this once. We have dx prime over dt equals dx over dt minus v. Now you see this is something that is fairly obvious, right? If you are moving away from let's say your house in a car, you see that for you it's going to look as if the house is moving away from you at some velocity, right? That is what this minus v is all about. All right. It's like you are stationary, but you see the house is moving away. But for someone in your house, let's say your parents are sort of waving you goodbye, they're going to see that you're going away from them. That's the kind of thing that we're looking at, right? So this is what Sagar wrote as u prime is equal to u minus v, where v is the velocity of the frame itself. All right. Now, if I was to differentiate this again, okay, I differentiate the velocities now. Du over dt minus, now we said, okay, let me write dv over dt. Okay, now we said that this moving frame of reference, okay, I'm finding it difficult to call it moving frame of reference and so on, so I'm going to name the stationary one as s and the moving one as s dash or s prime. Right now we said, like, our assumption here is that s prime is moving at a constant uniform velocity. Right, so that implies that this v, the velocity of the frame, isn't going to change with time, which implies further is that this quantity is actually zero, and what you're left with is du prime over dt equals du over dt. Now, if let's say if I assume a particle of mass m moving that is being considered, that is being studied, if I multiply both sides with m, what I basically have is that ma prime equals ma, or f prime equals f. Now, what this tells me is that the force that acts on the particle of mass m in the stationary frame s is the same force that acts on the particle of mass m in the moving frame of reference, provided that the moving frame is at a constant uniform relative velocity. Right, and that's why we put a strict condition that v here is constant, or you can also call it to be uniform. It doesn't change. Okay, and it is the relative velocity. Right, you have to measure your velocity with respect to something, and that's why this. So if let's say this frame was accelerating, then you would have some other force term here, and that force is what we observe in systems like rotating Earth, the Coriolis force, and so on, or the centrifugal force and the centripetal forces. All of those are a consequence of this, because the frames that we live in are actually non-inertial. Right, and this was Einstein's big problem as well. He devised special relativity, and it was very successful. It made super sense, mathematically. But then when you look at the real world, you realize that everything accelerates. Right, everything accelerates, and he thought about, should there be a speed limit? Can you just have infinite speed limit? And this again is a consequence of Newton's law of gravity. Right, and this is why Lorentz transformations were required. So I'm going to copy this diagram over to the next page. Control C, Control V. All right, let's just have it on a side here, and we'll just quickly discuss what was the flaw or what was missing in Newton's law of gravity. Okay, so what Newton's law told is F is proportional to or F is equal to G m1 m2 over r squared. Now, what's puzzling about this is the relation between F and r squared. What this equation implies is that if there is any change in m1 and m2 separated by some distance r, that change is immediately felt as the force. The problem was this puzzling thing of instantaneous reaction. Sorry about the spelling, instantaneous reaction, right? So according to this law, if the sun were to disappear at this very instant, I see that the time is 1840 to 642. So if it was to disappear at this very instant, we would feel its effects on Earth right away at 642, or now it's 643. right? That was a problem because special relativity's postulate said that the speed of the second postulate of special relativity said that the speed of light must be constant for all observers. Even information can only travel at the speed of light. So this was where there was conflict happening between what was already there and what is it that Einstein devised. Now, in order to accommodate this, he took the work of a completely different scientist, Lorentz. Right now, these Lorentz transformations were. Yeah, sorry. Go ahead.
So I have a question. Why there is R square? Why not R cube or something else? Why there is R square in the relation of?
That has to do with the kind of potential that we live in, and this was sort of derived from Newton. So I suggest you go back all the way to Newtonian mechanics, and then see the whole history behind why Newton told about the inverse square dependence on, of the forces of gravity. Going into that right now would be a great digression. So I don't want to go into that right away. But Newtonian mechanics is your answer. This is all classical physics, right? Everything that we're doing until now is still classical physics. We're not into the quantum realm. We're getting into relativistic classical physics right now. We're getting into the 1900s. But yeah, you see that this comes because the potential energy or the gravitational potential is a 1 over r field. Okay, and force is defined as the derivative of the potential. So if you do that, you get force to be proportional to 1 over r squared. Okay, so that's like a extra thing that you can go and study. I won't be getting into that right now. All right. So I hope I've been able to convince you as to why exactly did Einstein have to come up, had to take the help of Lorentz transformations, because Galilean transformations weren't enough. Galilean transformations implied that even in every inertial frame, the force, the information traveled instantaneously, which wasn't allowed by the second postulate of special relativity. So here we have the Lorentz transformations, and I won't be getting into the exact full derivation of it, but I will just tell you as to what motivate, how does it come up in how do we get these Lorentz transformation equations and what do they imply? Okay, so let's get into that. So again, we just take the same scenario that Sagar was explaining throughout. We have two frames of reference, S and S prime. S prime frame is moving at a relative uniform velocity of v with respect to S. Okay, now we have some event. Can all of you mute yourself, please? I hear some background noise. Please don't mind muting yourself. Wajid, I see your hands up. Do you have a question?
Yes, sir. It was a previously, sir. I asked the question, sir.
Oh, okay. So there's no question, right?
There is no question, sir.
Okay, you can put your hands down. Thank you very much. All right, let's get into this. So we'll assume some event that is happening at some point in time. Let's say you are moving out of your house in a car, and then someone's there at your home looking at you, and then you are looking back at the house, and all of that is already there. Now, let's say you watch, I don't know, a bird fly or something, or a bird come and sit down on a tree. We'll call that to be some random event, right? The kind of event is immaterial to us, but we just are concerned about the event that is happening. Now we have two frames of reference: you, who is moving in the car at a constant velocity, and someone at your home who is stationary. Right now, we'll observe this event from these two perspectives. Now, first we'll look at the perspective of someone who's at home, okay, which is the S frame of reference. From the S frame of reference, this event will have a x coordinate like so, and we'll call it x in S. Okay, x coordinate of event in S is equal to x, as simple as that. Similarly, for someone in S prime, their origin is O prime. So for them, this event is going to be, I'm going to mark it in blue, just this much, and that we'll call that x prime. So what I've written here is the x coordinate of event in S prime. And that we call it to be x prime. Right. Fairly simple. You're just giving locations to those. Now, you already have a relation with Galilean relativity that x prime is just equal to x minus vt, where t is the time taken to cover some distance here. This d, whatever that d is just v times t. So that's not that important. Okay, but this is what Galilean relativity tells us. Again, we assume that there is nothing happening along the y directions and the z directions, so they don't change. That's our assumption. It just makes our life easier. So y prime remains y and z prime remains z. Now here's where the Lorentz transformations actually start to make a difference. Galilean relativity said that time is absolute, time does not change. But in order to comply with Einstein's second postulate, time had to change in order to keep the speed of light constant. Right? It's like you can think of this as a very simple consequence. You have the formula: speed equals distance over time. Correct. Now, if you want speed to be constant and your distance is varying, then time must also vary. It's like a ratio, right? If one changes, then the other must change to keep speed constant. It's something like that. All right. So in that sense, Lorentz said that t prime is not equal to just t, okay, but is actually equal to, or let's say something. Okay, we'll leave that blank as of now. All right. Now we need one important thing that is to be satisfied if we are to have this set of transformation equations, which is relativity implies that the velocity is comparable to the speed of light, right? It's very high speeds, right? But when v is much lesser than c, which is low speeds, we already have Galilean relativity. Right. So this is like a very special condition that is to be imposed on Lorentz transformation, such that no matter what transformation equations you eventually get, for low speed limits, it must boil down to Galilean transformation equations. So with that in mind, I won't be getting into much details of this. You can convince yourself that x prime is proportional to x minus vt. Y prime remains y prime, z prime also remains z. Y prime remains y, z prime is the same. T prime should be proportional to whatever time is in the stationary frame minus v over c times x. Okay, this is done for dimensional purposes. V over c is a dimensionless quantity and so on and so forth. I won't be getting into the details of this, but this is what we sort of need. All right, and before we continue any further, we realize something that is very obvious but sort of ignored. All right. So let's say instead of an event here, okay, let's say I kept a piece of yellow scale, for example, or a yellow stick. All right. Instead of an event, we'll just assume there's a yellow stick lying there. Okay. Now, this is like fairly obvious if you know where to look for it. But from the first look, you probably may or may not guess it. But the fact is that the length of this yellow stick remains constant, right? We'll call this length L. Let's just call it L for this slide here, right? No matter if I observe it from a moving car, we'll just stick to this as of now. Okay, this is a very crude example I'm giving. I'm sure all of you are already aware of length contraction and so on, all those fancy things. But let's just push all that aside and just look at something very simple. Okay, let's not get too complicated and get too ahead of ourselves. The length of the stick is going to remain the same. Okay, so this is what we call an invariant quantity. Something that doesn't vary. Okay, we call this an invariant quantity. Now, after just figuring out how space and time works and blah blah blah, you can generalize this idea of an invariant quantity as ds squared. Okay, it's like your Pythagoras theorem basically. Okay, so if you have a triangle, okay, with sides dx and dy, then ds is going to be the same. So ds equals dx squared plus dy squared. But this is in 2 dimensions, and if you were in 3 dimensions, you're going to have a dz squared. Okay. Now, like we discussed in this section over here, if speed is to remain constant, then one of them must change. We've already dealt with distance. Dx, dy, dz are all distances. So now we need to make a compensation for time, and that is done as follows: as c minus c squared dt squared. C squared dt squared gives you the dimensions of length squared. So this entire equation is satisfied dimensionally. The minus is to, you'll further realize if you read it by yourself, that the minus sign is to preserve causality, so that the cause precedes effect. Right? So it's just that. But for our purposes here, we'll just understand it as compensation to keep the speed of light constant. All right. This is an invariant quantity. Okay, which means no matter what frame of reference you're in, this quantity ds squared is going to remain constant. And I think at this point, I should give you a little heads up that the rest of the session is going to be a little mathematical. So the ones who do follow, good. The ones who cannot, try to grasp the conceptual understanding of whatever is going on. All right. Okay, coming back to this, we have now defined our ds squared. In frame S, okay, in the stationary frame, we have ds squared, the invariant quantity, to be dx squared, dy squared, dz squared, minus c squared, dt squared. Okay. In frame S dash, right, this is the moving frame. This person would measure in a different coordinate system, which is the like we define x prime here, and then we define d prime here. We'll call this ds prime squared. And so this person is going to measure it as dx prime squared plus dy prime squared plus dz prime squared minus c squared must remain the same because the speed of light is constant in all frames of reference. So c squared remains c squared, but dt becomes dt prime squared. All right.
Oh.
And the fact that it's, yeah.
Okay. My question is, can you explain again why we use the Pythagoras theorem here to find out ds squared?
Yeah, I mean, Pythagoras theorem isn't exactly the correct way to look at it, but it just it just helps you to look at stuff in a little easier manner. It's basically how you calculate distances in your coordinate geometry, right? So if you have 2 points, right, x1, y1, and then you have x2, y2, the way you calculate distance between them is x2 minus x1 the whole squared plus y2 minus y1 the whole squared. Something like this, right? I don't exactly remember. Right. So what I've written here is like a manifestation of that. So if I was to square this, my d squared would be, if I call x2 minus x1 to be delta x, the change in x, plus, and then this would be delta y. Right. And if you had a third dimension in 3 coordinates, it would have been delta z squared. This is, Pythagoras theorem was just to make it simpler for the ones who don't already know about 3D geometry. So yeah.
Okay, in previous diagram, which 2 points we are going to consider? Can you show the previous diagram?
Okay, first let me get rid of the scale because that is not what we're doing here. Okay. We are just considering the coordinates of this particular event that's happening. Okay. So we have x prime here, and then we have x from the S thing. Okay. So if you were to sort of see the infinitesimal, the smallest amount of change that's happening, that's the ds squared thingy. Okay.
Okay. You meant to say the d distance. This is nothing but a small change.
Yeah, this is the change one. It's not the distance wala d. Okay, this comes from your calculus. This is like delta x, delta y, delta z, and delta t. Okay, where the limit, where the delta value, the change is so small that you can write it as an infinitesimal change, which is dx.
Okay.
It's like
Thanks.
the limit is tending to 0. So I made that clear, but yeah, thank you for bringing that up. It's an infinitesimal small change that's happened. All right, it's not to be confused with this d. It has nothing to do with that. Okay. All right, let's move on. So we have two invariant quantities in their respective frames of reference. Now, so the thing with these invariant quantities is that they remain constant. They remain the same in all frames of reference, right? So what we basically have is that ds squared is equal to ds prime squared. Okay, that's the consequence of having this invariant quantity. This is an advantage that considering invariant quantities gives us, is that they're going to remain same throughout. The length of scale is going to remain if I measure it in my car or you measure it in your house. That's how it works. Okay. It might get a little confusing. That's okay, because relativity is a little counterintuitive, but that's fine. Okay, as long as you understand, like, I don't know, 70% of it, that's more than enough. Okay. Now, before we proceed, we'll come back to our proportionality here, and we'll remove the proportionality by adding just a random constant. We'll call it gamma. Okay, this remains same, so I'm not going to deal with that. And t prime equals gamma times t minus v over c times x. Okay. So with that, if I was to put it all here and then do the substitution and then cancel stuff out, what we end up with is this. We end up with dx squared minus c squared dt squared equals dx prime squared minus c squared dt prime squared. Okay, you just substitute the expressions for ds squared and ds dash squared. You can cancel out dy squared and dy prime squared because they're the same, right? So I'm going to put that in red here. Since there is no motion in the y and the z directions, so is our assumption, there won't be any change in the y and the z direction. So it's fair enough to cancel them out. Okay, so I'll just move on to the next page. We have dx squared minus c squared dt squared equals dx prime squared minus c squared dt prime squared. Okay. In order to proceed from here, you just remember the fact that x equals gamma times x minus vt, and t prime equals gamma times t minus v over c times x. You differentiate this, you find dx prime and dt prime, and then you square them, right? You get something. I'm not going to do the entire math of it. Okay, and then you put them back, and eventually what you end up with is this. Gamma equals 1 over square root 1 minus v squared over c squared. And I'm very confident that all of you have seen this quantity, right? And this is called the Lorentz factor. It depends on, I mean, various authors call it different things, but let's just call this the Lorentz factor. Okay, this gives us the equations of Lorentz transformations. So we have x prime equals gamma times x minus vt. Y prime remains the same. Z prime also remains the same. T prime is given as gamma times p minus v over c times x. Now there are several things that you can notice here, where of course gamma is written as 1 over v squared over c squared under root. Okay. Now there are several things that you can notice here. Yeah, sorry, go ahead.
What is that gamma over there? X,
Okay, so that's like a proportionality constant that we added here, right?
Okay, thank you.
This is where gamma comes from. If you missed
Why
it.
we had same proportionality constants for x dash and y p dash?
Sorry, I didn't get that.
Why we use same proportionality constants for x dash and p dash?
Because the observers are relative to each other, right? So they're going to observe the same thing from two perspectives.
Okay.
Right. So that's one of our realizations. When you see the gamma thing, it doesn't depend on the coordinates. It only depends on v, and our v here is the velocity of the frame. Right. So it's independent of observers. So even if we had taken different constants, we would end up with the same factor. If I'd taken, let's say, alpha and beta instead of gamma at both places, I would get alpha and beta to be this. So it's like a back process that, we already know it's going to be the same. So we end up taking the same gamma thing. One thing is that all of this has been already done long ago, like 100 years ago. So you don't have to worry about redoing the entire thing to rederive the same expressions. But what matters is how you interpret all of this, how well you understand the interpretations of all of this. Okay, so I'll just write the two equations that matter to us, which is x prime and t prime. Okay, and if you guys are taking down notes, then these are the points that I would sort of like you to jot down. Right. First thing, I'll put them as arrows. X and t are interrelated. Do you see that? To find x prime, I need t, and in order to find t in t prime, it's dependent on x, right? So they're dependent. right? And this comes again as a sort of a manifestation of this fact, where we discussed that in order to keep the speed constant, the ratio must be changing. If distance changes, then time also must change in order to keep the speed constant. So we're like imposing that very strict condition that the speed of light must remain a constant. Okay, next we'll also look at the expression of gamma here. 1 minus v squared over c squared. Another condition for Lorentz transformation is that for low speeds, let's look at low speeds. Okay, when v is much less than c, if you take the ratio v over c, then that's going to be much less than 1, right? It's going to be a very small quantity. So I'll just rather write it as a small quantity. Okay, what happens to gamma then is that I'll write it as approximately 1 minus, this is negligible, so I'll write it as 0 under root. Gamma almost becomes 1 for low speeds. And when gamma becomes 1, my x prime just reduces to x minus vt. And here in t prime, this just reduces to t. Why? Because my v over c is a negligible quantity again. It's a very small quantity, so I can neglect it. Okay. So we get back our Galilean transformations or Galilean relativity equations. Right. So these are the things that you can deduce out of these things. So yeah, that brings us to an end of Lorentz transformations. If there's any questions, go ahead.
So if V is equal to C, then what happens to gamma?
Gamma goes to infinity, obviously, right? If V equal to C, then gamma 1 over, we can write this as C squared over C squared, right? That becomes 1 over 0, right? 1 minus 1 is 0, square root of 0 is 0, and that tends to infinity.
Does that mean these equations are invalid at V equal to C?
Exactly. That's again a very good observation. That is why in special relativity, in all kinds of relativity, we don't consider the case of V equal to C in real life scenarios, right? Anything that you observe always has a speed a little lesser than the speed of light, and you can always go ahead and study why exactly isn't speed of light attainable. Why can't you have V equal to C in real life scenarios? Like even if you have any particle apart from the photon with even a little bit of mass, it can never move with the speed of light. And the same applies to neutrinos as well. They have very negligible mass, but it's still not zero, right? So it's like a statement we make. Particles with mass equal to 0 move at c, and particles with mass not equal to 0 move at v less than c, always.
So is it rest mass equal to 0 or some?
Let's not get into the concept of rest mass as of now, because those are still further topics that we will be discussing. Right?
Okay, sir.
We will get to that eventually, right? We'll see what kind of mass is it and so on.
Yeah, my question is the neutrino has a speed greater than the speed of light?
That depends on what medium are you observing it in. All right. Now here again, what we mean by this statement, the second statement, is this in vacuum only. Okay. Recent research has shown that you can accelerate, I forgot which particle that was, up to 30 times the speed of light in plasma. Okay, that's this very specific condition. You can increase the speed of light depending on what kind of medium are you measuring it in. But in vacuum, C is the maximum limit. Okay, in vacuum only. This also is in vacuum only, because you know that when light enters water or glass or any medium with a refractive index, it slows down. You can calculate that.
Yeah, right.
So all these cases we assume are only in vacuum.
Okay.
What is this x in the t dash equation?
Sorry, this x here is the position of the event or the particle in the stationary frame of reference.
But it's not matching the dimensions of the equation.
Yeah, I might have messed that up. I think it's V over C squared. I might have messed that up, but the dimensions you can always not worry about. That's okay. You don't have to worry too much about dimensions, so it's fine. I think it's if I put V over C squared, I think it sets right? Does it?
Yeah, it's
Yeah.
V over C.
Yes,
Yeah.
yes.
But don't worry too much about the dimensions. Okay, that's like the least of our concerns. Always. Okay. These are what matters here is how these coordinates are transforming from one frame of reference to the other, which are moving relative to each other. Right. So that's about that.
There's a question in the chat, Vikrant.
I'll come back to the chat box later because the next section is going to be a little more mathematical. And I want to introduce this to everyone who's in the meeting today so that, they get a taste of how a bit of advanced relativistic physics is. Okay, I don't want to simplify this on purpose. Call me cruel, I'm sorry. But I sort of want to put this out there that relativistic physics is not always too easy to comprehend. Right? The mathematics might look very simple, but it's the comprehension, the way you understand it is what matters. Okay. So the topic that we're going to talk about next is about the structure of space-time. Okay. Or more, let me not keep it so general, but what we're going to talk about is something called 4 vectors. Some of you might be familiar with this, some of you might not. It's totally fine. Okay. Now, it's very simple, although, right? When I try to explain it to you, you will realize that it's something that you've known all along with just one addition. That's it. There's a slight modification there is. So in 3 dimensions, right? We have our x, we have our y, we have our z, random directions. Okay. And any vector here, let's call it r, has 3 components. Right? We'll call this r vector to have components xi plus yj plus zk, right? Now, once you study a bit of matrices and so on, linear algebra, it's called linear algebra in a bit more technical sense, you will realize that you can represent this vector as a column matrix, x, y, and z. That's it, right? It's like a simpler notation. Instead of having to write the I, J, and K every single time, we just choose to represent it as a matrix in a matrix form. It's easier to calculate matrices in higher dimensions. And what this allows us to do, right? This is a 3x1 matrix. But you realize if you've studied matrices that you can have matrices of any dimension, right? You can have an n cross n matrix, n rows and n columns. And this sort of generalizes your whole idea of space. Here we consider 3D space, which had x, y, and z directions. But trying to represent it in a matrix form sort of opens up the doors to n dimensions, right? You can have 5-dimension vectors, you can have 7-dimension vectors, you can have 11-dimension vectors, and so on and so forth, right? Similarly, instead of going to 5, 6, and 7, and so on, we are going to extend this idea of vectors. This is called a 3 vector, obviously, because it has 3 components. Okay, so we're going to add one more component to it, and we call them the 4 vectors. That's it. It's as simple as that. So 4 vectors have 4 components. And how do we find these components? It's fairly simple. We'll go back to our transformation equations. I'll just get rid of this a little bit. Here at x here. So we'll go back to our transformation equations. We have x prime equals gamma times x minus vt. We have y prime equals just y, sorry. We have z prime equals z, and t prime written is gamma times t minus v over c squared x. Now I've taken care of the dimensions as well. Okay. Now, by convention, only by convention, we prefer to write t first. Okay, the time is written first. Okay. Now I'm going to skip a few steps. Okay, I'm going to skip a few steps and I'm going to tell you that I can represent these components as, let's say, I don't know, I don't want to use the components that are actually there, but I want to make it simpler for you. I'm going to call them, let's say, A, B, C, and D. Now you see, if I was to represent this in a vector form, I can just write it as A, B, C, and D. And that is equal to, we'll see something that has to come up here, multiplied with X, since we're writing, okay, let's just leave it as that, X, Y, Z, and T. Here, we still haven't taken care of the convention, but that's okay. All right. So, you can represent these 4 equations in a matrix form like this. All right. Now we'll just have a look at how the matrix is, and I'll also introduce to you another convention. The components are written as x0, x1, x2, x3. These are not squares and cubes. Okay, that's the common mistake that happens. These are not squares and cubes, but they're just what do you say, labels. You can just call them as labels. They're not squared. So if I was to square this, I would write it as x2 squared. That would mean a square. Okay, this,
indices, no?
yes, these are indices. But for you, if you find that to be quite a complicated word, you can just remember them as labels. Instead of A, B, C, D, we put them as x0, x1, x2, x3. And from our previous convention, we define x0 to be the time component. Okay, and x1, x2, x3 are the space components. All right. This is all like a precursor to understand how relativistic mechanics actually takes place, right? So yeah, let's just go ahead. So with this notation, with these labels, we can write our Lorentz equations as x0 equals gamma times, x0 prime, right? X0 prime can be written as x0, or yeah, I think I wrote that correct. It will be x1. Yeah, it'll be x1 minus what is it? Why am I messing this up? V x0, and then x1 prime is going to be, oh wait, okay, that's why the mistake. Okay, so this is going to be gamma times t, that is going to be x0 minus v over c squared x1, and then we have x1 prime, that is, so this was actually t dash, okay, and then this is going to be gamma times x1 minus
V into
x0. Yes, thank you. I always, get confused sometimes with this. And then x2 prime is going to be x2, and x3 prime is going to be x3. So this was our x prime, this was our y prime, and this was our z prime, or this is x, y, and z coordinates. Okay. Now, using this notation, you can convince yourself later on that you can write them as so: x0 prime, x1 prime, x2 prime, and x3 prime in a matrix form, right? You can write this as gamma minus gamma beta 0, 0 minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 multiplied with x0, x1, x2, x3. Now I realize that this is a very huge jump from everything we've been doing so far, and it's totally fine if you're lost. I get it, because I was lost when I read it the first time, right? All that we've done here is all these components that we had. We have gamma here, and then gamma times b over c squared, and then again in the second equation we have gamma, and then again we have minus gamma v, and so on and so forth, right? So you can work out, I'm not going to work out, but you can convince yourself, or just take my word for it, that these 4 equations can be represented in a matrix form like so, where beta is just v over c. Okay. And this again can be simplified into a simpler matrix notation, the 4-vector form. So now we'll get into the 4-vector form. Let me just copy paste this.
Vikrant?
Yep.
You haven't used A, B, C, D that you have considered the convention here?
Yeah,
We
so
just...
so in that case, it would be, I just spoke that out, I didn't explicitly mention it. The ABCD would be like this if you were to compare it with the previous thing.
Okay.
Right? We have A to be X prime, B Y prime, C Z prime, D time. And so A would be X1, B would be X2, C would be X3, and D would be X0.
Okay.
Okay, so we'll have A here, B here, C here, and D here. You know, our convention that we chose was to write time on top. That's it. So that's why the D comes on top. There's nothing else.
Is it gamma times beta?
Sorry?
In the matrix.
Yeah, it's gamma times beta, where beta is V by C. That's just another shorthand notation. You just want, you don't want to write V over C every single place. So you just put beta.
Thank you.
So one thing that you realize once you start doing relativity is that Einstein was lazy half the time. Okay, he didn't want to write many things at the same time, which is why you have this shorthand notation, which I'm going to show you. Okay, instead of even writing these big matrices form, we saw that, you know, writing it in matrix form simplifies our life to several dimensions, right? But there is an easier way to write this, and that is as follows. You can write this as X prime mu, let me put the brackets, X prime mu equals, let me make it a little bigger so that you can see it. X prime mu equals lambda. This is capital lambda. If you're, let me not use that. Let me just use any other alphabet that you're familiar with. Since it's a matrix, we'll call it M. Okay? M for matrix, mu X mu. That's it. So I'll put the summation as well, where summed index is mu from 0 to 3. Now you realize that the entire huge big four-line big matrix and so on has been reduced to a very single line. Okay. This is where the definition of 4-vector comes in. Okay. A quantity like this, or a quantity like this are called 4 vectors. Why? Because they have 4 components. Okay, so if I was to write it in its component form, I would write X prime mu to be equal to, in the form of a column vector, as X prime 0, X prime 1, X prime 2, and X prime 3. Similarly, I would write X nu to be X0, X1, X2, and X3. There's no prime here, so I won't write the prime. That's it. Okay, and my M mu nu is just a matrix. Okay, those who are familiar with matrices, it's just another fancy way of writing Mij. That's it. Okay, where you have I rows and j columns and so on. And this summation implies you're summing over the index. So I won't get into details of all of this. Okay, so even if you don't get all of this, it's totally all right. It's just notations. But one thing that I do want you to take away from this part is how we write 4 vectors and how we define 4 vectors. Okay, 4 vectors are quantities with 4 components, where the first component is strictly time, and the rest 3 are space.
Yeah, Vikra, it just follows the same fashion in all the books, or it has some different fashion like?
Yeah, there's a slight differences that you will notice. So since you've brought it up, let me point it out. The convention that I am using is that my vectors that I'm using are of this form, X mu. Okay, I'll just write it as X mu, where mu goes from 0, 1, 2, 3. These kind of vectors are in some books called contravariant vectors. Okay, this is just, I mean, these are called contravariant vectors, and you have another kind where the mu comes downstairs. Okay, 0, 1, 2, 3. Those are called covariant vectors. Okay, and the difference here comes when you try to define it here, how you choose to write your components. So instead of writing these numbers 0, 1, 2, 3 up, I could have chosen to write them downstairs. Then all of these would be downstairs. This and all would be downstairs. This would be downstairs. X0, X1, everything would be downstairs. And this equation would look like, if I was to write it in the other form, X prime mu, matrix remains the same. Okay. And this would have come down. I should probably change the indices a little bit. Okay. Why I did that, it's fine. I mean, that's just how you play with indices. That's a matter of tensor algebra and everything, but so on. Okay, it doesn't matter. So you can choose to do this. Okay, I choose to do this, the contravariant thing. Okay, but if you look at electrodynamics, you call it the covariant formulation of electrodynamics because they use this notation. All of electrodynamics is sort of given in this notation, the second one. Okay, but you don't have to worry about that again. It's not that it's not of paramount importance, and you mess up things and so on. But there is a difference between them. Okay, there are rules which say how can you go from one to other. You can't simply do that. Okay, you can't simply change. If you have an equation, let's say x mu equal to something, you can't simply write that equal to x downstairs nu. You can't do that. Okay, there's rules that you have to follow in order to make sense. Why are there rules? Is because they are matrices. Okay, and you will realize from basic matrix algebra that if you have two matrices A and B, A dot B, if you multiply two matrices, it's not the same as B times A. Matrix multiplication is not commutative. That is why we have to take care of how we use these indices up and down, which is why I also changed it here. If I ended up putting the mu downs and mu sort of is up and down. So on. But indices again is a whole thing by itself. So let's not get into that right now. And with this, since we're almost out of time, I will just introduce to you the concept of momentum. Okay. Of course, momentum. Yeah, you had it out.
Yeah. One doubt. In the matrix, you have written that time is as a first. So it is the same fashion. It will follow in all the books that time is first. Then
generally, yeah. Generally, yes. Every book that I have read so far has time as the first component. But you may find places where time is just taken to be the fourth component. As in place of x3.
So it won't affect all the calculation.
Yeah, you just have to take care of how you're defining it and then just follow that definition. Right here, I've defined my x0 to be time. So in any calculations that I do further on, my zeroth component is known to be the time component. Okay, but if you define your 4 vector with the fourth component to be time component, then in every subsequent quantity that you define, you'll have the fourth component to be the time component. That's it. It's just purely definition.
Yeah. Okay. Thanks.
Yeah. In fact, you can even put it in between. You can tell x1 or x2 to be the time thing. It doesn't really matter. But one thing that you have to take care of is that when you write your invariant quantity, which was this, right? You can only have a plus, a plus, a plus, and a minus, or minus, plus, plus, plus. Okay. This is where the convention comes in. So let me rewrite it like this. Okay. Let me put the time component first. C squared dt squared. Then you have dx squared, you have dy squared, and then you have dz squared. Okay. The only allowed conventions, the only proper conventions are if you have minus, plus, 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 or you can have plus, minus, minus, minus. Okay, you can only take the red one, or you can take the yellow one. Okay, you can't mix red and yellow here. And when I say that you can define your time component to be anything in between, what I just mean is that you can call this to be x0, you can call this to be x1, you can call this to be x2, and you can call this to be x3. Or you can call this to be x1, this to be x2, this to be x0, and this to be x3. Okay, but whatever you do, follow that. It's just that. Okay. But since there are so many options available, we just stick to the standard convention that this is x0, this is x1, this is x2, this is x3, something that everyone is okay with, something that everyone would find it easy to work with. That's it. Even though there are several ways you can do it, right? You can shuffle around with the minus signs and so on and so forth. Okay, so yeah, that's about that.
I have one more doubt. My question is, he said that the special relativity is applicable when it is according to the Maxwell relation. Means in the Maxwell relation there is no inertia frame of reference. So speed of light is independent of frame of reference according to Maxwell frame of reference. So can you explain this? How these laws are valid according to special relativity?
Okay. For that, that's the whole subject of relativistic electrodynamics, right? That's the unification of relativity and how Maxwell's equations are invariant under these so-called Lorentz transformations. I will not be dealing with that today, but however, we do have a session planned next week for the gamma ray group, so you're free to join in on that. Okay.
Yeah.
In fact, Hardik and Sagar, are you guys here?
Yeah,
yeah. So since I haven't clearly been able to complete what I wanted to, I presume that the gamma ray group is currently free on Tuesday and Wednesday, right, Hardik?
Right. Yes.
So I would like to continue this on those 2 days, if that's okay.
Yeah, sure.
Yeah, and we can build up on relativistic electrodynamics eventually. So I'll stop it here. I don't want to overburden everyone else with velocity and so on and so forth. It would get a bit complicated from here on. So yeah, I'll stop here for today. And if you guys have any questions, you can. And the next session that I'll be doing related to these topics would be on Tuesday and Wednesday. Okay. Now, I realize that tomorrow's neutrino group is working on Mandelstam variables, right?
Yes, Vikrant.
Yeah, so for that, we'll have a quick, if it's possible, we can just start like 15 minutes early tomorrow. And I'll tell you what is required to understand Mandelstam variables, and then we can proceed to have our discussion.
Okay.
Okay, yeah. Okay. So ending it here today. I realize it might have been a bit too much for some of you, and a good refresher for the rest, for others. So do let me know how you felt, and if you have any questions. Yeah, sorry, go ahead.
Will you explain the Minkowski space of 4 dimension?
That is our
the topic that I was not able to understand.
Yeah, that's our very next topic. So I don't. We don't have enough time for that as of now. That is why I'm sort of restraining myself too much to continue, because I believe the gamma ray group has their meeting right now on Zoom, and we are to leave Zoom for them. And I don't want them also to miss out on these space times and so on, right? Otherwise, I could have offered to continue on Discord. But don't be saddened. I'm really sorry that I cannot do it right now. But we will do it on Tuesday for sure. All right. Meanwhile, you are free to read ahead. And if you haven't understood, then you can just text me on Discord. I hope you do know my Discord ID, which is VIKUU. So you can just tag me and ask me a question, and I'll be sure to get back to you on that. If you have any specific questions about the Minkowski spacetime.
Okay.
Yeah, Vikrant, I have one more doubt. That in this project we need a general theory of relativity.
You probably won't need it. I mean, the maximum thing you need is redshift, cosmological redshift. If you are trying to study data from, if you're trying to make sense of why gamma rays are losing energy when they keep coming to us. If you are doing that thing, I'm not sure. Hardik, maybe you can answer to that.
Yeah, we'll be doing that, so that even the Doppler shift also will be involved. So.
Yeah, so if you need general relativity, then yeah, we can have a discussion on that. That's not a big thing. All right, but you just let me know if you need a session on GR specifically. But again, for that, you'll have to we need to have a precursor session about what four vectors are again, and build it up to this concept of quantities called tensors, and then we have to understand how they behave, and then so on and so forth, because there's a lot of background that goes into understanding GR. Right?
Yeah.
Even if it is conceptual, you do require some amount of mathematics to show what is it that you're trying to tell. So yeah.
Okay, is it possible to take one small session on general theory of relativity to
Sure,
understand?
yeah, why not? Why not? But I don't think the right time for that is right now.
Yeah.
I think the right time for it would be after we've done relativistic electrodynamics, because for that we do require these quantities called tensors, which I'll be introducing then. So maybe seeing how free you guys are, we can plan a session or a set of sessions about general relativity, depending on how time is, how much time we have and so on.
Yeah, definitely. And there is one book, Gravity, the idea of Einstein. Is it good book for general relativity to understand basic
I
understanding?
haven't read that book specifically, but I can suggest you to go through Sean Carroll's book. I think it's called Space, Time and Relativity or something, if I'm not mistaken. Sean Carroll's book is pretty good. And then there's a book on gravity by James Hartle. Let me just write it down.
Yeah, I think so. That is the one book which I'm talking about. James Hartle,
Okay.
yes.
Yeah,
Gravity.
so Hartle is a pretty good book. I haven't read it per se, but I hear it's a really good book. And the other one is by Sean Carroll. I'm sure I don't know if I got his spelling right, but yeah, there's Sean Carroll. But if you want to get a conceptual understanding of relativity, special and general, Einstein himself has written a book on relativity. It's called Relativity. Right? It's very non-mathematical, and it's very sort of just lectures and paragraphs about what relativity is all about. Right? There's very little mathematics in it. Okay, so there's two books by Einstein. And these I can vouch for, they're pretty good. One is just Relativity. This is non-mathematical. There is a little bit of math, but it's not the actual math of relativity. And the other is called Meaning of Relativity. And this is mathematical. And surprisingly, it's smaller than the first book. In terms of number of pages, it's quite small. It's like maybe a little smaller than the first book.
I think this is kind of advanced thing.
Yeah, but they're
Meaning
pretty
of
good books. So if you want to go ahead, if you have interest, then you are free to explore all of this.
Yeah, definitely.
And if you want to get a good idea about these four vectors and tensors and all, there's a book by Ray D. Inverno. I forget the name of the book, but the author is Ray D. Inverno, and he pretty well, introduces you to these concepts of four vectors and tensors and so on.
I have a general off-topic, not
Yeah, go
off-topic,
ahead.
theoretical doubt.
Sure.
The special relativity second postulate is the result of Michelson-Morley experiment. And the first was a kind of we can get from Newtonian laws. Then what and why we are crediting Einstein for special relativity.
Okay, first thing is that the second postulate, the fact that speed of light is a constant, was not because of Michelson-Morley experiment. Michelson-Morley experiment sort of indirectly proved the fact. Einstein just assumed the speed of light to be constant. It was one of his hypotheses initially, okay, which later turned to a principle. Einstein was like, okay, there's all kinds of speeds lying around. But what about light? That seems to be something special. And there's a famous story that goes, what happens if I rode a beam of light? That's how this whole idea of relativity was born. And about the first postulate, let me just read. So the statement that I have here is that the laws of physics apply in all inertial reference systems. And yes, you do sort of get that from Newtonian physics, but what makes Einstein's relativity more special than Newtonian or Galilean relativity is that it also applies for high velocities without the loss of information, right? Newtonian relativity, like I told you in the starting of my talk, is that it hints towards the idea of instantaneous information sharing. Right? Let me just go back to that if I have it. Oh no, I erased that. Okay, so it was like I told you about the example. If you, I don't know if you were there in the talk at that time, but I gave this example of Newton's law of gravity, which said that if the sun disappeared at this instant, which is at 7:37, we would know its effect immediately, right? But that would violate Einstein's second postulate. I mean, that's why he started working on it, right? He was like, either one of these things has to be true. Either information travel instantaneously, or that the speed of light or the speed of information is a constant, right? Einstein believed in the second one. He assumed, he believed strongly that the speed of light has to be a constant, an upper speed limit in the universe. And that's how he was able to find out that no, it actually takes 8 minutes for the information from about the sun's disappearance to travel to us, because light takes 8 minutes from the sun to reach us. So that's why we credit Einstein with a proper, more good theory of relativity, rather than Newtonian and the Galilean relativities are like boiled down versions of Einstein's relativity, right? Whereas Einstein's case is the more generalized one. You can apply it anywhere. That's why we sort of credit Einstein for generalizing whatever was there.
Okay, so Einstein put it and take it from the trash that the speed of light is constant on the basis of all this information.
Yes, exactly. He based it on this. In fact, Newton, in his book Principia, Newton's book on all these laws of physics, also mentions about this trouble he's having about how exactly is gravity permeating between sun and earth if there is vacuum in between, right? He didn't understand as to how exactly is gravity, how are we being held by the sun? Is there some invisible rope? This is something that you see in pop science videos. Is there some invisible rope that is holding the sun and the earth together, right? This is something that even Newton puzzled upon, but he couldn't find an answer. Einstein did. That's why we credit Einstein with all these discoveries or discoveries that he did.
Okay.
Sir, I recently find out that the relativity of Albert Einstein fails during dark matter. Recently,
I'm not sure I've read about it, so I can't really comment on it as of now.
Okay, sir, it is okay.
Yeah, maybe you can just send that article or paper or whatever it is you've read on Discord, and I can have a look at it and I'll let you know.
Okay, sir. Okay, sir.
Yeah, just tag me so that I don't forget, because there's a lot of things. So
okay,
please
sir,
do tag me so that I can check it out.
Okay, sir. Okay, sir.
All right. Now, before we take further questions, I'd like to point out that the time is already 7:40, and it's time that we leave this to the Gamma group. So further questions, we can move to Discord, or if you guys want to learn Python, the people of the Neutrino group, you're free to stay behind and learn a little bit of basics of Python. And I believe Shivalik is giving taking the session, are they?
Yeah.
Yeah. All right. So without further ado, I'm going to stop sharing my screen, and I welcome Shivalik to take over and start off with Python. All the best. Have fun.
Thank you.
Yeah. So just like before he begins, I would like to say that he has volunteered for this Python presentation. So if anyone else wants to present for the next week's topic or the weeks after that, please let us know. You are free to do so.
Hardik, can you let me share?
I'm sorry. Where's Jivan? Vikrant, do you have the permissions to do
wait,
that?
yeah, 1 second.
Yeah, no, I'm not a host on this account. I'm sorry.
Yeah, okay. Anjesh is doing.
Yeah, Shivalik, you should be able to share.
All right. Yeah. Can you see it?
Yeah.
Okay, how do I stop this thing from preventing me from changing tabs? Okay, cool. So if any of you want to try this out, you can just go to Google, type in Jupyter Notebook, and you should find a link that leads you to a lab that looks like this. So you can just go to this website. It's called jupyter.org/try. and click on Jupyter Lab. And once you click on Jupyter Lab, it'll take some time to load. So once that loads, click on Python 3, and you should be able to follow along with everything that I'm executing if you want to. Yeah, so once that happens, it happens. Yeah, so how this will work is I have a presentation, and this will cover the theory part of it. And whatever I do here will be executed in this notebook. So I'll share both of these with you once I'm done. And if you need it later, you can look through that. Okay, let's start. So I'm assuming everyone knows what Python is basically. So it's a programming language. It's one of the most recent ones, and it's one of the most popular. So the language of Python is very high level. So what high level means is that it's very similar to English. So that way it makes it easier to program things because the structure of the code also follows sentence structure, kind of, but not really. But Python is also concise, which means you can do a lot with a little bit of code. So so there are a lot of modules and predefined things in Python that you can just import and use directly. So that keeps code small and readable, and it's simplified, which means things that are named in Python, for example, a function that you call or you use from another module will be named according to its use. So that way you can easily understand what a function does just by reading its name. Python is case sensitive, which means that if you type a small a versus a big capital A, they'll be treated differently in Python. And you should keep this in mind, especially when you're using variable names. The syntax of Python, it uses new line to separate commands. So if y'all are familiar with other programming languages, you will know that usually we use a semicolon to separate commands, and you can write multiple commands in one line just by putting semicolons in between them. But that won't work on Python because Python uses a new line to separate commands, and it uses indentation to separate blocks. So for example, if you write a loop or a conditional statement, you'll have to use indentation, that is a gap or a space, to convey what lies in one block. And if you remove that space, you'll be moving outside the block. So just to show you what that means, so a equals 5 is one line. And when you say print a, that automatically becomes the next line because you've moved to a new line. So how to execute this in Jupyter Notebook is just by pressing Shift and Enter, or you can use the run command here, right? So this is what new line means. So it moves to the next line to get the next command. And indentation means, for example, in this. So if I say if a greater than 6, and I put the semicolon, which always I put the colon, which always comes after a loop or a conditional statement or a function. Anywhere before you start an indent, you'll find a colon. And this gap here is the indent. So anything that I type with this amount of gap comes under the if. So you don't use curly brackets or anything of that sort to denote a block. You will only specify this gap, and this gap has to be same for everything that should be in this block, right? So Jupyter I've already shown you, but if you want to install Jupyter, which is what I recommend doing after this session, you can follow these links, which I'll be sending to you later. So it's pretty easy to install, although it might take some time because these are big files, but it'll be useful if you get it on your computer rather than using something online. So yeah, let's talk about data types. So data types are a way to distinguish between different kinds of data. For example, numbers and letters can be distinguished through data types. So there are numeric data types, which are numbers. So those are int, which are integers, floating point numbers, which are denoted by float data type, which is decimal numbers. And you have complex numbers, which we won't be using, I assume, but it's good to know that that exists. Text is stored in strings, which has the data type str. So a string is something that's enclosed in single quotes or double quotes, and you can type anything inside a string, and that won't be counted as a Python command if you put it in quotes. Then you have sequences, which are lists and tuples, which we'll talk about later. And Boolean is a binary variable that holds either true or false. So this can be used when you're checking for certain conditions or things like that. So the good thing about Python is that data types are assigned automatically. So you don't have to specify. In certain other languages, if you're familiar, you remember you have to say int a equals this and things like that. So when you use Python, it automatically assigns the data type of the variable without you having to mention that. And even though that happens, if you need to explicitly mention a variable as something, for example, if you want a equals 5 to be a float, there's a way to do that, and I'll show you that. And multiple variables can be declared at the same time, as in the same line, which is not available in another programming language. You can declare multiple variables. So let's talk about this one first. So I said variables are assigned automatically a data type. So if I say x equals 7, you would predict that this is an integer. So if I run this cell, it says that the type, this is what you use to find the type of whatever variable you're working with, which will become useful when you're using multiple different things and you're not sure what is what. It'll give you insight into what kind of data you're working with. So type of x is an integer. So now I say p equals hello in quotes. So now I told you that when you have double quotes or single quotes, it becomes a string. So this is a string, and there are a lot of string functions that you can use to manipulate strings, which are beyond what I'll be teaching you now, but it's good to look into that. And so this is how you explicitly mention what data type you want something to be. So you will say a data type, and the data type is not necessarily what you would call it. So I would say integer, but if I wanted the data type of integer, I would say int, right? So if I run this cell, you can see that automatically it becomes 3.0 because floating point numbers are decimal numbers. Now, variable names are also case sensitive, as I told you. So small a, small p, if I assign 4 and capital A, small p is true, then these are different variables. So if I run this, the first one is small a, small p, which should be 4, and capital A, small p is true. So these will never get confused with each other, and you should never assume that they are the same thing if you come across these things. Now, variable names, these are very important because there are certain conventions that you have to follow when you're naming your variables. So variable name must always start with a letter or underscore character. So you can't start with a number or any other special character. So you have to start with a letter or an underscore, although starting with the letter is the usual convention, which everyone follows. So a variable name cannot start with a number, and it can contain only alphanumeric characters and underscores. So you can have only A to Z, both capital and small letters, 0 to 9, and the underscore character. Some languages allow $signs and asterisks, I think, but those are not allowed here. So you can only use underscore as the symbol. And underscore is only used when you're separating words. For example, if you want to say new total or something like that, you'd say new underscore total. So that's the naming convention, which makes it easier for any other person who's writing code in Python to read your code and understand what's going on. So variable names are case sensitive, as I showed you already, and no special characters are allowed. So if I look at this, A, P, and capital A, P are allowed variable names. But if I try to start with a number, if I run that, it says invalid syntax because I'm trying to start the variable name with a number. So if I remove that number, it works, right? And this is how you declare multiple variables at the same time. So you just separate them by commas. So A, B, C equals 3, true, and pen as a string. So how this works is these are assigned respectively. So if A is first, then 3 goes to A, and true goes to B, and pen goes to C. So if I run A, I'll get 3. If I run B, I'll get true, and so on. Right. So now let's work on how to get input and output. So you'll be working more with output than input, because if you're doing anything with data, you already have the input and you'll be reading those files, which you'll learn tomorrow. But yeah, so if you need to input anything, input received through an input method. So any method is in boldface and italics, and any arguments are just in italics. So what an argument is something that you pass along with a method. So this is an optional string, which means that if something is optional, then you can leave it out if you want to. So generally, this optional string is used to tell the user what kind of input is expected. So I would say input, and in this bracket, I would probably give enter a number if I wanted a number, or enter a string if I wanted a string. So I'll show you how that works. Then this input method always returns a string. So if you say s equals input, let's show you that. So if I say s equals input, then it'll ask me for an input. And if I give the number 5, and if I check the type of this, it's a string. because input always returns a string type. So you should keep that in mind, because if you input S and you type 5 and you try to do addition or subtraction with that, you will get an error because it's inputted as a string, but you want it as an integer. So how do you do that? Is through typecasting. So typecasting is when you forcibly change the type of a variable. So that is done similarly to this, how we used float here, where typecasting this 3 to become a float, even though it would have automatically been assigned as an integer. So we do the same thing here. So here, this is the optional string that I was talking about, where you say enter a number. So, and I'm typecasting that as an integer because this input is coming as a string. And if I typecast that as an integer, so now this text is what is the optional string. And if I type 5 here now, I've inputted 5. And if I check the type of that, it's now an integer because I've typecast this string to become an integer. So now I can do any operations I want with that. But the same thing, if you try to typecast something that's not a number, then you'll get an error because you can't change D into a number because it's not a number. So make sure you know what you're typecasting and how you're typecasting it. Output is, also raw input is an older method that's used to get specifically strings. And if you're using an older version of Python, you need to use this if you want to input a string, because otherwise these string functions won't work. Although you won't be needing it, but I've just put it here. Output is produced using the print method. So you've seen me using this print method the whole time here. So this is what I'm talking about when I say Python is very simple and easy to understand. It's a high level language. So when you want to output something, you just say print. When you want to input something, you just say input, so that it's easily readable. That's why it's so popular. So you just use print, and within the print statement, you can pass anything. You can pass a string, you can pass a variable. Anything that can be printed will be printed using print. So for example, if I say K and L as high and 5, I want to print both of them, it prints both of them. And in, for example, in Java, you use a plus to separate things that need to be printed, but here we use a comma. So in Python, every print thing is separated by a comma. So if I want to print K, L, and then I want to print the string high, I can just do that and it'll print that. Yeah, so you use commas to separate them. Now, if you want to do any kind of mathematical operation in Python, you'll need to know operators and expressions. So they mean the same thing that they do in maths. An expression is just a collection of variables and numbers with operators. So for example, x squared plus 5 is an expression. And plus is the operator there. So there are different types of operators, but I've only chosen 4 types here, or 5 actually, which you'll be using most commonly. So there are logical operators, which you won't really be using, but they're there just so you know. So arithmetic operators are the regular operators. Those are plus, minus, multiplication, division. This percentage symbol here is a modulus, which means it gives you the remainder of something. So if I say 5 modulus 2, 2 2s are 4. So 1 is left as the remainder. So you get the answer as 1. And this double asterisk is a exponent symbol. So this basically says to the power of. So if I say 2 star star 3, that'll give me 8, which is 2 cube. Assignment operator is equal to. Everyone knows what that is, but you should just know what it's called in Python if you want to talk about it. Relational operators check for equality or any kind of comparison between 2 things. So if you want to check if 2 variables, let's say A and B, are equal to each other, you'd say A equals B. This exclamation here means not. So A not equal to B. So if you want to check if 2 things are not equal, you would use not equal to. Then these are less than, greater than, less than equal to, greater than equal to, which are regular meanings. What's special in Python is the identity and membership operators. So identity checks if your variable or whatever you're using the identity operator for is something else. So there's an is and an is not. These you won't be using that frequently. What you'll be using more frequently is membership operators, which you'll see more of when we come to lists. But that basically tells you if some variable or some number is in some collection of something else. For example, if I have a list of numbers from 1 to 5, I can check, I would say if 4 in list, and that would give me true. But if I said if 6 in list, then it would say false. So those are membership operators, which checks membership of any variable in something. So this is just how you use operators. So if I say s is 5 and t is 6, s minus t should give me -1. And is s equal to t? It's not. So I get false. And s to the power t is this huge number. That is 5 to the power 6, right? Are there any questions so far? No, okay. So let's talk about lists. So lists are basically, if you've done any other programming language, you'd know arrays. And lists are like arrays, although they are not arrays. So don't think of them as arrays. Think of them as just lists. So there are lists. There are a list of things. They can be anything. A list doesn't have to contain the same data type. You can have a list of integers mixed with floats, mixed with strings, and objects as well, and anything. So how do you create a list is either you use square brackets. That's like this. So you can say L equals, open your square bracket, put whatever you want to put in your list. I've used only numbers, although you can use anything else here. So if I print this list, it comes out as it is, right? So this is a list, and the list is always identified by square brackets. So that's a list. And you can also use the list constructor, which means, okay, I haven't done it here, but you can just say L equals list like that. Wait 1 second. Yeah, so when you're using a list constructor, you have to use 2 brackets. So when you type L, it just comes as 1, 2, right? So that's how you use the list constructor, and this is how you use square brackets. Square brackets is easier, but sometimes when you're not sure of what the elements are and how many elements there are and things like that, you generally use a list constructor. So lists are ordered, which means that they have indices. So index, you learned that like in the previous session. An index is just a number that's used to identify something, right? So the first element of a list always has the index 0, and then it goes on from there. So 1 would have the index 0, then 1, 2, 3, 4, and 5. So there are 6 indices, although they start from 0 and move to 5. So if I want the first element, I would call L of 0. So that's how you use indices. You put them in square brackets. So if I type L of 0, I get 1, which is the first element. Let me just change this to A and show you that it would work the same way. Yeah, so I get the first element, right? So that's how you use indices. Now here, if I say L of -1, now I told you indices only run from 0 and go up. So if you see a negative index, that means you're working from the back. So if I say L of -1, that means the last element. And if I put -2, that should give me 5, and so on. Right? So negative indices are used from the back of the list in case you want to quickly get the last element and you don't know how many elements are in the list, then you can use negative numbers to go from the back. Now the length of this list is given by this method len, which shows you the length of this list, just in case you want to know how many elements there are. So lists are going to be very useful when you use anything really. So you use lists quite often in Python. So it's good to know these basic methods and how to use them. So you can access them through the list name followed by the index and square brackets. So another thing you can do with lists is slicing. So slicing means taking one part of this list out. So if I take L from 1 to 4, now you'll see that I get 2, 3, and 4. So we know the index of this is 2. The index of 2 is 1, and 3 is 2, and 4 is 3. And I've only gotten those 3 elements. So my indices have stopped at 3. So you'll notice that if I slice from 1 to 4, the last one is not included. If I wanted to get 5 as well, I'd have to change this index to the next index, and then I'd get the 4, these 4. If I wanted the last one, then if I type 6, then I get all the way to the end. Another easy way to do this is without typing 6, is if you want to go from somewhere to the end, you just leave the ending blank. So if I want the second element till the end, I can just leave that blank and I get 3, 4, 5, 6. If I want from the first element till, now if I say 3 here, it stops at the second element. So if I want 0, 1, and 2, then I leave the first one blank. So if whichever one you leave blank, it assumes either end or beginning, depending on which one you left blank. So how do you work with lists? So once you create a list, you can add items to the list using 2 methods. One is insert and one is append. So they work in different ways. When you use insert is used when you want to add an item into one particular position in the list. For example, if the list has 6 elements and you want to add it at the 3rd position, you would use the insert method, provide the index that you want to add this in, that is the 3rd index from my example, and item would be what you want to add. So if I wanted to add the letter A as the 3rd index in the list, I would put insert 3, A in quotes, right? So that adds that specific item at whatever index I have specified. Append works in a different way because append just adds whatever item to the end of the list. So if you don't care about where it goes in the list, you can use append and provide the item as the argument. So that will just put it at the end. But if you want to put it in one particular place, you would use insert and you provide the index and the item. So let's say I have a list with 3 numbers, 1, 3, and 5. So the index of 1 is 0, index of 3 is 1, index of 5 is 2. So if I want to insert something here, I'd say insert 1. So this is going to be the index. So if I say 1, that means it's going to come here, right? In between 1 and 3. And I want to put 2 in between 1 and 3. So if I run that method and I print A, in Jupyter Notebook, you don't have to say print when you're trying to display something. If you just say the variable name, it will come out. So you get 1, 2, 3, 5. So 2 has been inserted between 1 and 3, where we thought it would be. But now if I append 6, we said append adds it to the end. So we can see that it's been added to the end of this list. So how do you remove things from the list? You can remove them using remove, pop, or clear. So there are 3 ways, 3 methods. There's also the del keyword, but that's not used quite often. So I'm teaching only these 3. So remove deletes the specific item. So what it does is it looks for that item in the list, and wherever it finds it, it deletes it. It removes it from that list. Pop removes the particular element at some index. So the difference between remove and pop is remove removes an item. So how it does that is it uses the membership operator that we learned about. So it checks if item in this, and then it removes that item. So when you use remove item, you get the list as the new list with that thing, with that element being removed. But if you use pop, what pop does is it gives you that element. In addition to removing that element from the list at that particular index, you also get that element. So let me show you that. So the list currently is 1, 2, 3, 5, 6. So if I remove 5 and print the list, I get 1, 2, 3, and 6. So it's removed 5. But if I pop, if I put 0 here, that means first element. So if I pop 0, I get the first element. And if I print A over here, it's also removed the first element. So if you want to remove an element while still knowing what that element is, you will use pop. But if you want to remove that element and don't care about what that element is, then you'd use remove. Right? And clear just clears the entire list. So you're just left with an empty list. Okay, so now we'll move to conditional statements. So conditional statements basically means that it checks for a condition. Let's say you have 2 variables and you want to see which one is greater. You'd say if A greater than B, print A, else print B. So that follows language like English itself, right? So you'd say if A is greater than B, then A, else, which means if not that, then B, right? So you have if and else. The condition always returns a Boolean value, right? So it either returns true or false. You can't have anything in between. Either A is greater than B or it's not, right? So the A equal to B condition will automatically fall into else, and the less than condition will also fall into else, right? So if you want to specify those 3 separately, then you'd have to use nested conditional statements, which means not nested actually, you'd use a ladder. So you'd use one condition. So you check if A greater than B. And if not that, you use something called elif, which is shortened version of else if, which you use in other languages. So if I show you this here, so I've given A and B as 4 and 8. And now if A greater than B, is A greater than B? No, 4 is not greater than 8. So nothing happens because I haven't specified an else condition. So if A greater than B, print less, and it won't print less because it's not. Now with an else condition, if I say if A greater than B, print less, else print more, that means if A is not greater than B, it will print more, and it has printed more. Now, if you want to check for equality as well, if I say A equals B equals 5, so both of them are 5, this is another thing you can do in Python where you can assign multiple things to the same, multiple variables to the same value by using equals in between them. So the variables would always come on the left and the final value that you're trying to assign would come on the right. This could also be a variable, but that variable should already have a value. So assignment works with what you're assigning to and what you are assigning, which is on the left and on the right. Right. So here I'd say if A greater than B, print less, elif. So this is allowing me to give another condition saying if A is equal to B, print equal. If they're not, print more. So automatically you can see that the else condition means lesser than. Yeah, so if I run this, it says equal because A is equal to B is equal to 5. If I change that, if I put 5 and 10, then it print more because B is more than A. That's what we're checking, how B compares to A, right? Okay. Now, I told you about logical operators, which are and or. There are also more logical operators, but you don't need them. So and or are only usually used in case of conditional statements, but sometimes in other places, but mostly here. So what this does is when you want to check for multiple conditions at the same time, you use and or you use or, depending on what your condition is. So if you want both the first condition and the second condition to be true, that means you want A less than 6 and B less than 9, you'd use an and. So if either one of these was false, that means if A wasn't less than 6, it would automatically turn to false even if B was less than 9. But if you want to check one or the other, you'd use or. So if A greater than 6 or B less than 9, which means either A can be greater than 6 or B can be less than 9, or both of them can work. So in that case, you use an or. So now we see, I need to change this back. A is equal to B is equal to 5, right? So now I have A as 5 and B as 5. So if I check this, A less than 6, 5 less than 6, that should be true. 5 less than 9, that is also true. Right? So you get a true. But here, if I change this to greater than, then nothing happens because there's no else condition, right? So this has automatically become false. And since I've not given an else condition, there's nothing that it can print. So because this was true, but since this was false and we've used an and, the net result of this statement comes out to be false. But if I do the same thing here, 5 greater than 6 is false, but 5 less than 9 is true. But since I've used an or, the net value of this statement comes out to be true. Right. So next we move to iteration. So iteration just means looping statements, which means doing things over and over again. So for example, if you have to run the same code on multiple different variables, you can put those variables in a list and put that list into a loop. So that's where you use iteration. So it repeats parts of code. So there are two types of loops in Python. One is for and one is while. So these work very similar to the ones you've already learned in other languages if you have. And we'll go through their syntax now. But loops can also be nested, as in you write a loop inside a loop. That's what nesting means, writing the same type of thing within that same type of thing. So there are 4 parts to a loop, which you should always make sure you have. So first one is an initialization, which means if you're using any kind of variable or a list or something in a loop, you should make sure that there's something in that list because you can't loop over an empty list. you should have a test condition, which means you have to check whether that loop should be executed or not. Otherwise, your loop will go on forever, and unless you have a test condition. And you should also have an update statement, which means that the variable that you're testing should constantly be updated. If it's not updated, then if the first condition turns out to be true and you don't change anything about that condition, then it'll constantly be true and you'll be stuck in an infinite loop again. And you also have the body of the loop, which is basically what you're trying to repeat. So that is the part of the code that you're repeating over and over again. So the first one is a for loop. So for is this keyword that you'll use just to declare that it's a loop. So for loop is used generally. This is not a hard and fast rule, but this is the general convention followed, that for loops are used when you know the number of iterations, that you know you want to run this loop 5 times, or there are 6 elements in this list and I want to run this loop only for those 6 elements. So when you know the number of iterations beforehand, we generally use a for loop, although it can be used for unknown number of iterations as well. So you can loop through an existing list, or you can loop through a range. So range is this function in Python that just gives you a range from any number to any number when you put those 2 numbers as arguments here. So I'll show you what that looks like, but let's go through the syntax first. So how you write it is for some variable. The general convention uses I, j, or k. So for I in whatever list, and I'm saying run this code. So how many ever elements are in this list, that many times this loop will run. So here you can see I'm using in, which is the membership operator. So for I in list name, I'm using a colon for any. So if you look at conditional statements as well, we keep using colons, right? So it goes if condition colon, elif condition colon, else colon. And after all of these colons, you can see that there's a indentation to show that this comes under that specific statement. So whatever comes under a for statement will be in that specific for indentation. So you can use a list, or you can also use a range from 0 to 5. That means it will go 0, 1, 2, 3. And just like slicing, it stops at 4. It does not reach 5. So it includes the first one, does not include the second one. So you can think of this as closed on this side and open on this side. Right? So if you look at the for loop, this is a list that I made from 1 to 5. And I'm going from for I in L. That means I will take up all the values that are in L one by one. So if I print I, it starts with 1, then it goes to 2, then it goes to 3, then it goes to 4, then it goes to 5. So you can see that these are not being printed in the same line because this loop is being executed 5 times. And each time you call the print statement, it automatically starts a new line. You don't have to specifically declare that it should go on to a new line. So this is the list. For is the keyword, I is the variable that I'm using. Note that you don't have to declare this variable or anything of that nature. When you say for I, automatically memory for that variable is created. In is the membership operator, L is this list that I've declared. Use a colon for conditional and iterative statements. This gap here is the indent. And after the indent, you put what you want under the statement. So just say print I. This gap isn't something that you should worry about so much, because as soon as you type a colon, when you press enter, it automatically gives you the specific indent that you need. So it'll come by itself. So if you're not using a list, you can use range. So for I in range, this range, what it does is it essentially kind of creates a list, but it's not a list in the sense that there are square brackets around it. It creates a range object, which you can make into a list, which I'll show you. So anyway, so if you're talking about range, this is a function that gives you a range from 1 to 6, and the default step is 1. But if you want to change the steps, as in you wanted to go from 1 to 1.5 to 2 to 2.5, you can add that here as 0.5, like that. So it goes beginning number, ending number, and step size. So I'll remove that for now. So if I print this, it goes from 1 to 5 because we know that the first one is included, the last one is not included, right? So this range function is particularly useful for creating lists, as I said. So you use a combination of the for loop with the range function to get a list. So let's break down the statement. So A is the variable that I'm using for the list, equals is the assignment operator. I'm using square brackets, which means that I'm creating a list. So what's inside this list is X, which is another variable. That is X for X in the range of 1 to 6. So let's start from here. Let's just take the loop. So if I go for x in the range 1 to 6, you know that I'm going from 1 to 5, right? So that is this part of the statement. When I put x here, that just means that whatever comes out of this, make that into a list. So if I run this, I automatically get a list from 1 to 5. So this works in the case where you don't know these numbers. Obviously here 1 and 6, so you know it's 1 to 5. But in case you don't know these numbers and they're being input by the user or something, you can use this to create a list easily. So let's go to the while loop. So a while loop is usually used when you don't know the number of iterations beforehand. And here you can explicitly see that there's a condition and update statement. When you looked at the for loop, you couldn't really see any initialization or an update statement or a condition or anything like that, but those are implicitly built into the loop, so you can't see them. But a while loop is a good example to see this, because here, so now I said a equals 0, which is the initialization part, that I'm saying a equals 0 initially, and I'm saying while a less than 3. So here is my condition. While a less than 3, I'm saying print this letter W. So that is the body of my loop. And a equals a plus 1 is my update statement, which if I don't change this, then 0 will always be less than 3. So if I remove this statement, 0 will always be less than 3, and this loop will go on forever. So to find a way to stop that, I have to give it an update statement, which is a becomes a plus 1. So how many times can a add 1 to itself until it reaches 3? It's 3 times, right? So 0 plus 1 becomes a 1, 1 plus 1 becomes 2. And then you get 3 of these outputs, right? Now, let's see if I don't give a condition. So I'm saying while true. So true is always true, obviously. So if I run this, you can see that it's printing a forever, right? And this won't stop. And this is something that causes a lot of errors in a lot of programs, and that people can't really figure out why this is happening. So if something's happening that you don't know where to find, go look at your loops, and it's most likely that there's some infinite loop running, and so you're not getting any output, right? So how do you stop this? If you're using Jupyter, there's a stop button here. So you can just stop that cell and it stops running infinitely and you can move on with your life. But sometimes you might want to create an infinite loop, in which case a while loop is the ideal candidate for creating an infinite loop, right? So let's move to break and continue. So these are two keywords. So there are keywords, which are just used as words, and there are functions which have brackets with them. So keywords are, these two keywords are break and continue. So these are used mostly in combination with loops, although they do have applications outside, but loops are where they are mostly used. So this break statement is you'll just write this word break, and it's used to terminate a loop prematurely. So if a loop is running and you want to stop it at some point, you'd write break there. And it's usually used when you're testing for something within a loop. So suppose I gave you a list that you didn't know. So there's a list from some number to some number. And I'm going to ask you to check if 5 is in that list. So the easy way to do it would be if 5 in list. But if you didn't know how to do that, you'd want to go through that entire list and check if 5 is there. So you'd say for I in list, if I equals 5, break. So what that does is, as soon as you find 5, it stops, because otherwise you're wasting time going through the rest of the list when you've already found 5. So that's where you use break. So here, for example, look at this. So there are fruits, and I've said apple, banana, and cherry. So for X in fruits, that means X takes on apple first, then banana, then cherry. And I'm saying if X equals banana, then break. So once we find banana, we're going to stop this loop. So if I run this, you'd expect that I can only get apple, because once it prints apple, you will see the indent here that all these indents match. So all of this comes under this for loop. And when you want to so I'm doing an if within a for, so this gets a double indentation because it's going under another, it's an indent of an indent, right? So when it reaches banana, I'm breaking. So it doesn't print banana because I'm breaking before the print statement. If the print statement was above this, if it was here, then it did print banana and then break, right? Because first I'm encountering print and then only I'm breaking. So break is used in cases like this. Next is something we call continue. So continue is like break, but the thing is it doesn't stop the loop entirely. It just skips one iteration or one cycle of this loop, right? So here, instead of break, if I said continue, so when I said break, if I move this print back, so when I said break, I got only apple because it stopped that loop and it never reached cherry at all. But if I use continue, then it goes to apple, it prints apple. When it reaches banana, it continues, which means it stops the loop right where continue is and goes to the next iteration of the loop, which makes X cherry and it prints cherry also. So this is used obviously when you want to exclude some specific item or some result from being printed. So this is where you use break and continue in loops. So now we'll move to functions. So functions are a very, very, very important part of programming. The majority of your programming will be written in functions. So functions are just blocks of code that performs a specific task. So now I can give you the example of the most basic function that just adds two numbers, right? So I can write, if I write a function that adds two numbers, I won't have to write the code for adding two numbers over and over again every time I want to do it. I just use that function. So we'll see how to do that. But a function is only executed when it's called. So once you write a function, if you execute the function by itself, nothing happens. You have to call that function. And how do you call a function is by using its name. So once you call the function, only then does the function start running. Until then, the function is just a block of code. So functions are static until you call them. Right? So function can accept parameters as input and return an output. So for example, I'll just show you this. So this is add, which is a function. So how do you create a function in Python is you use the def keyword. So that stands for define. So you're defining a function. And this is the name of the function. You can give anything here. Generally, we obviously give meaningful names to whatever function we're writing. So this is used to add two numbers. So I've given the name as add, right? So add, and I've opened and closed two simple parentheses. So every function is followed by an open and a closed bracket. That's what marks it as a function, right? And this is a colon because we are relating a block. So I've specified A and B as 3 and 8, and I'm printing A plus B, right? Then I've created another function sub, which is for subtraction. And here I've given arguments. So anything within a function bracket is called an argument. And these, in place of A and B, you can type any number or send variables with values across. And what happens is it uses these arguments in the rest of the function. So now suppose I passed 4 and 5, then A takes the value of 4 and B takes the value of 5. And this happens only when I call the function. When I'm not calling the function, these are just random variables that are here to hold the place of whatever will be input later. And here's the product function. And here, instead of printing it, I'm returning it, which means that whenever you call the function, you can also get the answer back instead of it just being printed. So if you want to do some calculation with the answer, then you'll have to return the answer instead of printing it. So now when I run this block, nothing happens because these are, as I said, functions are static until you call them. So until I call add, sub, or prod, nothing happens to this. So if I call add, it automatically gives me the answer 11 because I've already given the numbers here as 3 and 8. So it adds 3 and 8 and gives me the answer. But for subtract, so if I don't give any numbers and if I just call sub, I'll get an error because here I've specified that you have to pass two values as arguments. So the numbers you want to subtract are what you will pass here. So if I pass those numbers, I get 5 minus 2, 3. So how this works is when I say sub, it automatically finds the function named sub somewhere in this notebook, and it's here. So it finds sub. Then it sees that sub has two arguments. So it replaces the value of A with 5. So you get A equals 5, B equals 2. And this happens only when you run the function. This doesn't happen before you call the function. So this is what is a function call, by the way, where you write the name and you pass in any required arguments. So 5 and 2 are my arguments. So A equals 5, B equals 2 happens automatically. And then A minus B is done, which is 5 minus 2, and it prints that as 3. Similarly here, when I'm doing prod, so since I'm returning this value, if you're returning a value, then some variable has to be there to accept that value, right? So S in this case is that value, and S equals prod 4, 6, because I've said I need 2 inputs. So 4 and 6 are my inputs. And if I print S, I get the product of these numbers, right? So these are functions. Functions, there are a lot of inbuilt functions as well, which you will be calling from time to time during when you're writing your code. But you'll also be writing your own functions, which are called user-defined functions. So let's move to modules. So since Python is open source, anyone and everyone can write code that can be stored and used later by any random person, right? So there are a lot of modules that are extremely useful in Python because it saves you a lot of time from thinking about how to write your own code and what is the most efficient way to write your own code and all that. For example, if you wanted to, if I gave you a random list from any numbers and I told you to sort it in ascending order, you would have to loop through the list, find the minimum, and then there are lots of sorting algorithms. So you'd have to do, you'll have to use a loop and all of these things just to sort this list. But there is predefined code for sorting a list, and there's the function called sort. So if you just use list.sort, your list automatically gets sorted without you having to do any of the manual coding for that. So similar to that, there are a lot of modules which contain ready-to-use code. So that's what makes coding in Python so easy, is because you just go to Stack Overflow and there'll be the entire code of that whatever specific thing that you're trying to do, and you can just put that into your program. For example, if you're I don't know, trying to, let's say, find the redshift of something given some data. So if you look that up, most likely you're going to find a function that does that for you. So you can just call that function without having to think of, is this the best way to write this code? So how do you include modules in your program is using the import keyword. So import is a keyword that is always done at the beginning. Like for example, in C, you say include your header classes, right? So similarly, you have import keyword, which you always write at the top of your program so that you input whatever you need and you can use that later. If you don't import your module, you won't be able to use it. You'll get an error saying no module named this, right? So you can include modules completely as the whole set, but those are really big modules with a lot of code. So unless you're going to use a lot of functions from one specific module, I'd recommend that you only import them partially. That is, you import whatever you need and leave out the rest. So I'll show you how to do that. So modules contain classes, which also have functions and other variables and stuff that you'll need to use. And some common modules that you'll keep using once you start coding in Python are math. Math is automatically included. You don't have to import it, but it's good to know that it exists. Then you have NumPy, which is numerical Python. You have SymPy, which is symbolic Python, SciPy, scientific Python, and Pandas, which you'll be learning tomorrow, which is very important for data analysis. SciPy is very important for like scientific calculations and stuff, because it has all the mathematical stuff that you'll need to do scientific computations. SymPy is symbolic Python, which is used mostly for algebra. And if you're writing any kind of expression, you'll use SymPy. NumPy is numerical Python, which is used for things like matrices and stuff like that. So you can also create your own modules. If you want to put it up somewhere, you can put it up. But if you're writing a huge program, suppose you're building some kind of software, you can write your own modules and keep them aside so that you can call them into other parts of your code. Right? So if you look at modules, these are some modules, for example, NumPy. So you can import NumPy. Generally, we import them as some kind of, we give them a name. So since NumPy is really long, you can import NumPy as some, it's called an alias. It's a fake name or a pseudonym, which you use for the rest of your program. So you should make sure that if I write NumPy here now, it won't work because I've imported it as NP. So I have to use NP. And NumPy has a lot of things. For example, it has the value of pi if you ever need to use that. So I said a is equal to np.pi, and if I print a, I get the value of pi. Similarly, if you move to SymPy, what changes is, so I'm saying from SymPy import star. So here I said import NumPy as NP, which means that I have to use NP everywhere I'm using NumPy. When I say from SymPy import star, so what star means is star means everything. So I'm importing everything from SymPy. And when I write it like this, it gives me the freedom to not have to remember the name of this thing and what I'm doing. So I can just say p equals pi. So I won't have to say something dot pi. It would be sympy.pi if I didn't say from SymPy import star. If I just said import SymPy, I'd have to write sympy.pi. But here I'm saying from SymPy import star. So everything from SymPy is being imported, which means that the compiler automatically knows that this whatever I'm writing has to be from SymPy. Right? So if I say p equals pi and execute that, I get the symbol pi because we were working with symbolic Python. Here we're working with numerical Python, so the number came out. So depending on what your use case is, either use NumPy or SymPy. SymPy also has variable names predefined in it. So it's in this class called ABC. So this is how you import specific things from modules. So I said that if you're only going to use one or two things, import them specifically. So this is how you do it. For that, the thing is you need to know the class name and function name or whatever you're trying to use. So ABC is the class name in SymPy, which contains all these variables. So I've imported only X, but from A to Z, all variables are available to you in this class. So I've said E equals X into X. So X, so this is how you do algebra, right? So when you say X into X, that means X squared. So when I print E, I get the expression X squared. And there are a lot of things that you can do with this. For example, substitute a value or differentiate it, integrate it. All of that is available in SymPy without you having to do anything other than write the function name called diff for differentiate or integrate for integration. So it's a pretty useful module to learn about NumPy and SymPy. So learn those basics before you move on to more complicated things like SciPy or AstroPy and things like that. So lastly, I want to teach you about arrays. So like I said, lists are not arrays. Arrays are a different thing that are defined in the NumPy module. So why should we learn arrays and not just lists? It's because arrays have a specific use case in that. So now in the previous session, conveniently, you learned about vectors. And Vikrant said that you can write a vector as a column matrix, right? So a column matrix in Python can be written as an array, right? So how do you write that is I'm importing from NumPy import star. So you don't have to write NP or NumPy anything here. So I'm saying A is array, and I'm put this list here, which makes it an array. So to create an array, you need a list. So the list becomes an array A, and this list becomes an array B. And with this, I can do vector operations like a dot product. So if you find the dot product of this, you can see that it turns out to be 11. But if I just use lists, this dot product does not work, right? So if you're doing any kind of vector calculus or things like that, you want to work with matrices and all of that, you will have to use arrays and not lists, right? So arrays have similar functions as lists. They have, they work with the same indices thing, and you can slice arrays, and you can find the length of arrays, and everything else is almost the same, except that they are more mathematically defined, and they have a lot more functions available to use with them for more mathematical and scientific calculations. So if you want to learn more about Python, I've added a few resources here. Obviously, this class is not meant to be self-sufficient. This is just an introduction, and you'll have to do a lot more experimentation on your own, digging on your own. And if you have a doubt, then the best thing to do, I would say, is just execute it yourself and see if this works or it doesn't work. And when it doesn't work, the good thing is once you get an error message, if you just paste the error message in Google, I'm 100% sure somebody else has had the same issue. So you'll find a solution more or less. And yeah, that's it. So if you have any questions, you can ask them.
Can we use W3 Sukul, sir?
Can we use what?
W3 Sukul for Python. Is it good?
Yeah. So tutorials point, WW3 School, and Geeks for Geeks, I think, is a good website to learn those.
Thank you, sir.
Yeah, can you suggest or recommend some online course or videos on YouTube or something to like for beginners to start the Python?
Yeah,
by our
YouTube
own?
has a lot of courses. So I've linked to 2 textbooks here. These 2 are textbooks for Python beginners. And I haven't checked on YouTube, but I'm 100% sure that there are a lot of Python beginner courses on YouTube. There's one from, I don't remember the name exactly, but I saw one that was really good. Just go search online and you'll find a lot of them. You can find them in multiple languages also if you need it.
Okay, thank you.
But I'd rather suggest than doing something on YouTube, try to do a course on like Coursera or something where you can actually get assignments and stuff, because that'll help you practice rather than just watching someone do it. And if you get lazy, then you won't do it and all of that. So do something like that.
Yeah, like, do you have any specific course in your mind right now for?
There's one from University of Michigan which says Program for Everybody.
Yeah,
Learning
Programming
Python.
for Everybody.
Yeah, that one. That one's a really good course. You can do that.
Okay. Thank you.
You can also try out a course in Udemy, which is like Python from zero to hero, and it covers the basics really well.
Okay.
Thanks, Alan, Grant, Anurup, Shituja, Rizul.
Yeah, Shivada, you're really good, man.
Why does nobody have any questions?
No, they need to practice first, no?
Yeah, that's true. Actually, unless you do something, you won't have a question. So
a very small doubt, like for
yeah.
practicing platforms like HackerRank and all are like really good now. Like I know the syntax and all. Where I lack is like the practice part, like applying this knowledge.
Yeah.
So platforms like HackerRank and all are like good, not like okay. So that's all.
If you want to practice, there are lots of opportunities. Just go search for beginner projects in Python. You get a long list of things you can try out.
You can also check out the website codingbad.com. You'll get some interesting questions.
Yeah. Kushal, I'll send it across and on Discord after this session.
Hi, Shivalik. I have a doubt. When you talked about when you defined the add function, you defined a and b as 3 and 8.
Yeah.
If we don't do that, we only define add, then print a plus b, and then we invoke add 5 comma 2. Then will it? What will it give?
Oh, okay. Wait 1 sec. So what's happening here is there's A and B up ahead somewhere. So I'm just going to give some different things. So now when I call it, it will just give you an error because you've not passed TL and ML and it doesn't know what it is. So if you want to use that way, then say TL equals 5 here, ML equals 9. And now when you call it, these have been defined, so you can use the function.
Okay, I have a doubt. Another. When you, if we go back to the previous one, like we define A and B as 3 and 8.
Okay.
Then we then again invoke add function, and in the bracket we put 5.2.
Oh, so if you put arguments, then it's not going to take it because when you defined the function, nothing was given. So it says add takes 0 positional arguments, which means it doesn't take any arguments, but you gave 2. So the errors in Python are also very explanatory. So if you just read this, you'll immediately know what is going wrong.
Okay. If we then define add a comma b, like it has to take 2 arguments.
Yeah.
Then,
so if you put a comma b here, now the thing is, whether you pass it or not, since you've redefined a, b here, 3 and 8 will be the value that it takes.
So if we give 5.2, then the 5.2 will be changed to 3 and 8.
Yeah, exactly. They get reassigned.
Okay, thanks. Thank you very much.
All right, guys. I think if you have any other questions, you can ask. Yeah. Otherwise, I think we can end the meeting here.
Wait, I have to share something.
Okay. Sorry. Yeah. Go on.
Yeah. Yeah, so this is this week's activity. So we have divided everyone into 3 groups randomly. It's purely random. So since it's 3 groups, one group will have 11 members, the other 2 groups will have 12, and each group will have their the 3 separate topics. And so each group, what we have decided is that since to divide the work, each group will have 2 divisions, presenters and article writers. So presenters will be making the presentations and then they'll present, and article writers will write the article and the topic. So the division is left to you. It's like we won't interfere. Who on the number is everything is up to you guys. And submission and presentation date is on Monday, this coming Monday, 7th June. So you will have to submit. I'll be opening up an assignment portal in the LMS, and then you have to submit there. And also you'll have to present. Only one person, or it's up to you how many of you want to present. Also, and so totally there will be 3 presentations. See, and the articles will be uploaded in the Naxxatra's blog. So be creative, be stylish, and be informative, since it'll be going public. And topics on the member list are uploaded in the Discord channel. I have made 3 channels in the server for the 3 groups, and I have uploaded the topics and the member list in the respective groups, so you can check them out and you can start working. And yeah, so on Monday you'll have something. That's it.
I have a question, sir. Hello.
Yeah.
Why there is not what we call a voice channels for our groups, separate groups?
Wait. I'll create. Sorry. I've created text channels. I have to create the voice channels. I'll create.
Okay. Thanks.
Yeah. Oh yeah, and this is for 150 grade points for this week, and the rest 100 is from your weekly review. So which you have to submit on Sunday.
I think we all want to mention to them about topics again, just so that there's no sort of confusion.
All right. So the first group will be talking about the why EM waves are. The advantage of EM waves as messengers. You can talk about the entire spectrum. You can so like how do we detect also, you can just briefly cover it up. So the second group will be talking about the higher frequency EM waves and the lower frequency like sources. So how do they get produced? If you want to talk about optical also, it's up to you, but generally we suggest you talk about gamma rays to UV and from infrared to radio. So they'll be talking about the sources and how they are produced and how we will be detecting them. And the third group will be focusing more on the gamma ray bursts, GRBs. And so they will be talking about how you detect those GRBs from the outer galaxies. Mostly you won't be able to detect most GRBs from Milky Way, so we'll be talking mostly about the outer galaxies. And so these are the 3 topics I have put up in the text channel, so you can check them out later. And also I have made leaders for each group. This is also purely random, so you can communicate with each other, and the leader can take decisions. For the presentations, I'll be uploading a common theme, so which you'll be following. You'll be using to make the theme presentations, all the 3 groups, just to for consistency. Yeah. If you don't have any more doubts, we can stop to this session.
Hello.
Yeah.
Yeah.
Hello.
So I would like to this presentation that was taught to us today of Python. It would be really helpful.
Yeah, I'll just send it on the group.
Okay. Okay. Thank you so much. Thank you.
Shivalik, you can send it on the Lounge and the Cafe channel, the text channel, Lounge and Cafe. You can send it over there so that it's available to everyone.
Yeah.
Awesome. Great job. Thank you all for joining in. We'll conclude today.
Yeah.
And we'll see you tomorrow.
Bye. Take care.
Take care, guys. Stay safe. Bye bye.
Bye bye.
Adish, you can end the meeting. Stop recording.